Yes. Do you have any questions from the last times? Hmm. Now let's start. Last time we have learned about Booleanization and uh, mm, I will talk about some applications of it later. For example, about Booleanization of a Turing model, or vice versa, a harmonization of Saint Gordon. But today I wanted to tell about more constructions of this kind, and then we will apply them. And, namely, I want to tell about Kac-Moody algebras and their realizations. Uh, I already told that we can consider fermions with some other symmetries. Example, we can consider fermions. We can consider complex fermions of this kind, psi alpha, sum over alpha, from 1 to n plus complex conjugate. Or we can consider the same for real fermions. Psi alpha d bar psi alpha plus complex conjugate. And it will correspond to GLN or U or UN symmetry. And this corresponds to SON. Well, GLNC, SONNC, or SONR, depending on on whether we want some real structure on this. So there are these fermions, and they have a kind of obvious OPs, because it is just some addition of a index. So OPs will look like psi star alpha of z, psi beta of w is delta alpha beta over z minus w plus a regular, and psi star alpha of z psi star beta of w will be just a regular, and psi alpha of z psi beta of w will also be regular. So there are such relations. And when n was 1, we had a current J of z, which was psi star psi. It was some current of dimension 1, and it was responsible for holomorphic version of translation symmetry in the target space. But now let us study the general n case. So, namely, we can consider a currents G J alpha beta equal to psi star. So here it was normal product of psi star psi star alpha of z, psi beta of z. Это J alpha beta of Z. So let us compute OPs of such currents with psi star alpha. So let us write something like so it's definition. It's OPs and let us compute here the OP of this current with psi star gamma. So J alpha beta of Z with psi star gamma of W. What do you think? What we will get in the answer? Mm-hmm. But what do you mean by contract? Mm-hmm. Yes. Thanks. And what else will we, yes, beta gammas. Mm. So what else will we have? Mm-hmm. Yes. Thanks. Mm. So and we can write under this formula some formula for the action of J-line algebra on the vector space. So we have formula like E alpha beta acting on E gamma equals to delta delta beta gamma E alpha. So and here we have a kind of Chiral version of this formula. So in particular, we can ask, so there are this modes of this current. So we can say that J alpha beta of Z is a sum of J alpha beta n divided by Z to n plus 1 for integer n's. And which this? So E alpha is a vector with zeros and 1 on position alpha. So it's alpha. E alpha beta is the matrix mm, with 1 at one place, and this is alpha, and this is beta. No. This is but let me write like this. No, alpha beta. This is beta. This is alpha. So, there are this always generators of GLN. Yes. Basis generators. So there are n square of such matrices. So is it fine? Okay, so now the question. So if you have such OP, what will be the commutation relation between the modes of this J and the modes of psi? So what are the commutator? So psi alpha star of Z is sum over integers, half integers 1/2 plus z psi star alpha b over z2 plus 1. So what is the commutator of j alpha beta n with psi star gamma p? What do you think? Yes, yes. Okay. Hmm? No, why? How? Let us compute on this. Uh, maybe here. We have this OP. We have mm, maybe it's easier to compute a commutator of J of some mode of J with this full expression. So commutator of J and alpha beta with psi star gamma of W. It is the it is the difference of two contour integrals. So one contour integral is for absolute value of z greater than absolute value of w. Another with minus sign is for absolute value of z less than absolute value of w. And here we have dz z to the n over 2 pi I. J of j alpha beta of w of z psi star gamma of w. So these integrals can be shrinked to single integral around pole, right? So this equals to the integral integral z to the n over 2 pi I around z equals w. And let us substitute here this OP, so it will be delta beta gamma psi star alpha of w divided by z minus w. Yes. So what does it equal to? Mm-hmm. And for arbitrary and how? We are integrating around, these two integrals, so this was the integral for z greater than w. And this integral was for z less than w. And when we subtract them, we get integral around z equals w. So why is it important whether n is greater than 0 or n less than 0? Yes, because this integral, the difference of these two integrals reduces to a counterclockwise integral around the pole of the LP around z equals w. So it substitutes w, it substitutes z equals w simply. So and it doesn't matter what kind. Yes. Hmm. Delta beta gamma psi star alpha of w. So, what does it transform to if you perform a mod expansion of psi? What is the effect of this multiplication by w to the n? Mm-hmm. Yes. So, we will have this delta beta gamma psi star alpha p plus n. So, what is it? And in particular, we see that if we take if we take zero modes, they will not multiply this psi star by w, and they will not shift this index. So zero modes act precisely like this. So we will see their commutation relations, but even well, it's enough to know these relations. Is it? No, no, it's not enough yet. But we see some suggestions that this zero modes act as a usual GLN algebra. So they act precisely like this. So J alpha beta 0 in conjugation with psi star alpha p is delta psi star gamma p beta gamma psi star alpha p. So the action of a usual GLN algebra, right? But let us now compute the OP between these J's. So J alpha beta of Z, J gamma delta of W. Mm. And let us first S. So let me write the definitions of W. What is the most singular term of this OP? Hmm? Mm-hmm. 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 Yeah. Thanks. And what other terms will we have? So there will be a term where when we pair this two sides, right? So it will be Z minus W uh, delta beta gamma J alpha delta of W. And what else? So we pair this and get product of these two. So, what else can we have? Hmm? Hmm. Yes, with minus sign because they appear in the wrong order. First psi, then psi star. We should exchange them, so there will be minus sign here. And J beta gamma, gamma beta, sorry. W over the minus W. So let us now do the same. Let us compute mm, commutator of this Jn alpha beta with this J gamma delta of W. Alpha beta. So here, as before, we have some integral with the first order pole, and we can do a shortcut using this result. So we can write the first term simply as W to the n delta beta gamma J alpha delta of W minus delta alpha gamma J gamma beta of W. Right? And there will be another integral which we still need to compute. It will be the integral around W z to the n divided by 2 pi I delta alpha delta delta beta gamma over z minus W squared. So and what does this? So what will we get for this integral? So it will be delta alpha delta beta gamma times what? Hmm? Mm-hmm. Yes. Oh, like this. Hmm? So if I write the left hand side, uh, so maybe we can do the same with all of all these terms. So this will equal to sum over m uh, delta beta gamma j alpha delta m minus delta alpha gamma j gamma beta m over w to m plus 1. No, m minus n plus 1. Right? And so it in this term. And this term will equal to, oh, no, sorry, I would like to shift this index by n. So I would like to write here m plus n and here m plus n. So, and this will be m plus 1, like this. So, and here it will be a commutator of it will be a commutator of Jn alpha beta sum of alpha beta. I'm switching this order from time to time. No, let us say that it is the same. Gamma delta m or wm plus 1. So this equals to this plus this. Well, let me write it better. Delta alpha delta delta beta gamma w to the n minus 1 and w to n minus 1. So what can we say about the commutator of these modes themselves if you look at this formula? So what are the commutator of j alpha beta n j gamma delta m in terms of modes of in terms of modes of j? Mm-hmm. Mm-hmm. Minus or plus n? You mean with comma, m minus n, right? Yes. Okay, yes. Mm-hmm. Yes, yes. so this no, so this delta should be alpha delta gamma beta plus delta. So there is on this algebra, uh, and you see that it is like so. Mm, we see this relation, and we understand principle that if we put here some arbitrary number k which is equal to 1, then it will still be well-defined algebra, because Jacobi identity is satisfied independently on this k, in a sense that if it was satisfied for k equals 1, it will be satisfied for arbitrary k. Hmm? Yeah, yes, thank you. And delta m plus m 0. Now we can multiply it by some number. And suppose some complex number. So this is called affine Lie algebra. Affine GLN at level k. So another, so it's not not a complete synonym, but such algebras are also called Kac-Moody algebras. But when people say Kac-Moody, they can mean that there is also a degree operator added to this algebra. A degree operator added to this algebra, like L0. So operator that is commutator of uh, well, basically if we add here L0, it should be called Kac-Moody algebra, but sometimes these words are used as synonyms. So we can conclude. Hmm? Mm-hmm. Yes. Yes, from the Fifth-Hermans. Yes, of course. And it is quite easy to construct some examples with different keys. So what? Notation for this algebra is the following. So it is called GLN. Well, maybe we can put here C. It doesn't matter. GLN hat at the level K. So level is indicated here. So if you want to construct something k equals to So if we want to construct a k some some non-negative integer number, then we can simply take n copies of these fermions. From L equals 1 to k, psi star k L alpha of z psi L beta of z. Is it clear that we get a sum of k's? Yes. Hmm? So we can we take k copies of this n component fermions. So in total there are k times n fermions. No, but a important question is how to construct this J's. You can, for example, exchange alpha and L and construct not even different K, but a different algebra. No. So if you take K equals, so if you label them by the pair of indices, then and to construct some algebra, it will be just one algebra, right? No. So, but no, it's a question. What precisely we want to do? No, it's another construction which I'll tell at some moment. But for now, if you just label them by a single index, so if you write a sum from, so if you write some j alpha L beta, no, L alpha and beta, so we can write something like this. Yes, we can construct such currents, and they will form Cosmode algebra gel k times n at the level 1. But this is simply a statement that we can embed this algebra at the level k into bigger algebra at the level 1. Hmm? Hmm. What do you mean? What is precisely the problem? Uh, is it a question about complex versus real or not? Yes, it simply adds, we can multiply psi star by inverse matrix, psi by just a matrix, and it will be a symmetry of the section. Hmm? But I don't care about anti-homomorphic fields. We can simply write everything. Mhm. 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 We can no, we can say that one is transformed by uh, uh, by fundamental representation of GLN, another by anti-fundamental representation. Yes, yes. So we work with fermionic path integral, so we don't even care about possible divergence. So and these fields can be independent. Mm-hmm. No, the theory is the same. We can simply act with some larger algebra without any restrictions. So, hmm? Mm, unitarity means that we can add here complex conjugation, which keeps this action real. So this complex, so it means that we can act with this complex conjugation on this algebra, but it will transform something like homomorphic currents to anti-homomorphic ones. Mm, mm. Because complex conjugation of homomorphic function will be anti-homomorphic function. So. What do you mean by we should? Uh, so, oh, but we see that this action has this extended symmetry with homomorphic parameter. So, mm, mm, uh, I didn't think about this, but probably. So if they are direct fermions, we have psi stars and psis. I think we can act just by GLN, and it will not break anything. Mm. But here, for example, if you try to restrict to UN, there is a lot of problems because uh, this UN condition is this UN condition includes complex conjugation, and we will need to satisfy. We will need to solve an equation U dagger U of Z equals to 1, which will restrict us to I think only constant matrices. And this GLN can be made homomorphic algebra. So, But concerning these questions about GLN versus UN, so it is important, well, not very important, but can matter when we work with some group transformations. Uh, but if we switch to algebra, then we will just have some generators lying in the UN. And then we have Hilbert space on which the separators act, and we always consider everything complexified. Um, in quantum mechanics, in quantum field theory, everything is defined over the complex numbers. This algebra will be complexified automatically. So, and at the level of complex algebras, there is no difference between SUNC and GLNC. So, I mean, so let me write it. So, SU N R algebra times C is the same as as GLNC. So it's a statement that if you take a Hermitian matrix and multiply them by arbitrary complex numbers, we get all matrices. So is it okay or not? Mm-hmm. It depends. Oh, the statement is that if you have a theory of a kn kn fermions, it has a lot of symmetries. So there are different algebras acting on this Hilbert space. In principle, we can use any of them because it is a free theory. So if some symmetry exists, then nothing can happen to it. But then we can try to switch to some interacting theory, or to consider some operators that break this symmetry. So there can be some operator that break this bigger symmetry, but keep this one, which is smaller. So maybe some for harmonic interaction. But actually, I don't know if it is possible to deform it in a nice way. And also another remark about all these algebras. So here we are thinking about this gel n versus gel n k. But if you look at the commutation, I didn't write any commutation relations on this fermions. But the point is that all infinite dimension fermionic algebras are isomorphic because we have anti-commutation relations. Let me write it. So we have anti-commutation relations of this kind: alpha p, psi alpha p, p psi star beta q equals to delta alpha beta times delta p minus q. So all these modes anti-commute in the same way. And we can construct isomorphisms between n-component fermions and one-component fermions. And this is precisely what can be obtained using a special kind of twist fields, which correspond to an n-fold cover. So. A statement is that n-component fermionic algebra, as the abstract algebra, is isomorphic to this mode algebra of single fermion. So we can take all these modes of n fermions and put them like 1 to 3n, 1 to 3n, 1 to 3n, which corresponds to n-fold cover. So we can say that there is some Riemann sphere covered like this. There is some branch cut. So, and this n-component fermions appear as push forward of a single fermion that lives on this n-fold cover. And so, in terms of modes, it means a fractional mode with denominator n. So fractional part of this mode will correspond to the number of fermion, and integer part will correspond to a fermionic mode. But maybe we'll study such things later. I just wanted to show that there is such phenomenon. At least it should be expected. So, in particular, it means that we can realize any Cosmode algebra with integer k or on in the Hilbert space of a single fermion. So we will need to use such tricks where when we separate modes of this fermions into n different components. But it is doable. So the statement is that many different algebras can be realized on in terms of this simple one, in terms of a single complex fermion. Or maybe we can even go further and say that it is a single real fermion, because a complex fermion is a pair of real fermions, and the pair of real fermions is the same of a single real fermion. So, but it is not some nonsense. It is something that gives rise to different kinds of twist fields, and it can give some trivial representations. Sometimes. Okay, but let us now think. Are there any questions about this? Okay. Let us. Mhm. Yes. So we simply need to divide this mode into different fermions. But the remark is that such constructions are constructions of this JLN hatchet the level K as some Lie algebra, because all this separations to different fermions do not respect the structure of the vertex separator algebra. So even in this simple situation, when we switch from n-component fermion to one-component fermion, there is some map like psi star of z equals to psi 1 star of z to 1 over n. So there will be such kind of transformations that act non-trivially on the argument. There will be some branched covers. So it is not embedding of vertex separator algebras. With this twisting. So any other questions? Okay. Okay, but now let us probably also show another theory, namely W model, which also has this symmetry. But at the moment, let us forget about fermions and say that we only have some theory that has this symmetry. So now we have just this J alpha beta and J, well, let me write it as the OP. J alpha beta of Z, J beta gamma of W, gamma delta, sorry. K delta alpha, also beta and gamma delta. Alpha delta, delta beta gamma. By the way, I forgot to mention. So, is it obvious that gel n algebra, in a sense, non-affine algebra, lies inside this affine algebra? Is it obvious that non-affine algebra is a subalgebra of affine one? Hmm? Yes, yes. So this central extension vanishes, and we get simply this relation. It was probably no, I didn't write this relation between E alpha beta, but it is precisely this relation for zero modes. So there is this GLN C in there. And by the way, how would you write this relation in the arbitrary algebra? G of z, GB of W equals to, so something so the same, and so what should be the generalization? So for example, what should we write here? Hmm? Uh, if it is some arbitrary algebra, then it has some scalar product, not necessarily a diagonal one. Oh, so some GAB, invariant scalar product on the Lie algebra, in Killing form, for example. And what should be here? Mm-hmm. Yes. Mm-hmm. Yes. Yes. Hmm? Yes. Thank you. So. For example, we can check that this real formulas give precisely this algebra, and it will be a sole n. But it is maybe kind of clear that we will have two more terms because they are uh, they are all of the same sort. Maybe it's not very interesting to study them separately. Okay, but now the question is, suppose that we have some theory with this Cosmode algebra symmetry. Can we construct its energy momentum tensor? So when n was equal to 1, we could construct this energy momentum tensor considering just j squared, 1/2 of j squared, right? So, and can we have something like this here? Actually, so maybe let us say that this metric will be identity matrix. So maybe it is the simplest option, especially computationally. So I propose to consider an energy momentum tensor of this kind. T of z is some coefficient, maybe over 2, as before. Mm. So here, this algebra is already non-commutative, and we cannot use the usual CFT. We cannot use the usual normal ordering. So we should use a CFT normal ordering. So it will be a sum from a equals to 1, well, sum over a over all generators of this algebra, GA of z GA of Z with some unknown coefficient, because as we will see later, this coefficient will be non-trivial and we need to compute it. So we want this energy momentum tensor to be the actual energy momentum tensor. But maybe before that, it is easier to ask this J's to be primary fields. And let us maybe start from this question. Hmm? Yes, it's a question because in principle, if we take if we take just discuss Moody currents and construct energy momentum tensor from them, it can be energy momentum tensor of some sub theory in the CFT. There will be some fields that commute with this energy momentum tensor. So the only requirement is that this is some energy momentum tensor. So so it for example, what kind of example can we consider? For example, if we take a U1 case, we can have J1 and so on, and Jn with diagonal P, J1 of J of Z, J of Z equals to delta Ij over Z minus W squared. And we can construct J of Z equals to 1 over square root of n probably. Oh, let me think. So maybe 1 over let's go J diagonal. So what is the OP of this J diagonal with itself? Let me write it here. What will it be? Yes. So now we can construct a diagonal energy momentum tensor. right? And this diagonal momentum tensor. So what would be what will we have for the OP of this T diagonal of Z with J diagonal of W? Hmm? In the diagonal. Mhm. Mhm. So it is the primary field of this energy momentum tensor, right? Uh, and so if and but what happens if we now compute the OP of this energy momentum tensor with itself? What will be the first term? Mm-hmm. Yes. Uh, Force plus the other terms. So we have some CFT with central charge n, because we have n currents, and there is some energy momentum tensor with central charge 1. What does it mean? It means simply that this way we obtained only some subalgebra in the algebra of all fields. In particular, there are fields J. So the question is, what is the OP of this energy momentum tensor with Ji of Z minus uh, J of W minus J of W. Mm-hmm. Yes. So we see that this CFT consists can be represented as sum of two CFTs. So, and in terms of energy momentum tensor, we can write it as energy momentum tensor equals to T diagonal of Z plus T non-diagonal. Uh, but what does it equal to? Uh, yes. So we can first ask what is the OP of J diagonal with this difference. Hmm? Mm-hmm. So J diagonal. Mm. So uh, and uh, well, and since this is regular, then this is also regular. And this is some example of coset construction. So, so this is so we can write this energy momentum tensor of non-diagonal. We can write this energy momentum tensor as difference T of z minus T diagonal of z. And what kind of cassette is it? It is a GL1 hat, how to write the tensor, or maybe tensor. I don't know what people usually write. GL1 hat divided by GL1 diagonal. So it means the following: we can take some bigger algebra and take some subalgebra. For example, this diagonal one, and then we can consider only the fields which commute with the subalgebra. Uh, and say that energy momentum tensor that describes this subtheory is a difference of original energy momentum tensor and the energy momentum tensor of this diagonal algebra. So if we do this, it is easy to see that this non-diagonal energy momentum tensor commutes with subalgebra, right? Is it obvious? Because because if we take some operator which is in this GL1 head diagonal, and then OP of T of Z with this O of W will be, or if it is primary field, then it will be some delta O over Z minus W squared plus dO over Z minus W. But it is so OP with diagonal energy momentum tensor will be the same of Z O of W will be delta O over Z minus W squared plus dO over Z minus W. So if you now subtract this, then T of Z minus T diagonal of Z with this O of W will be regular. So in this particular case, this set is generated by some combinations of gi's with zero sum of coefficients. So it's like we take vector 1, 1, 1, 1, 1 in this n-dimensional space, and consider some plane which is orthogonal to this vector. But one of the main points here is the following, that if we took some fields that are present in our theory and constructed some energy momentum tensor, so that these fields are primaries for this energy momentum tensor, and it is actually an energy momentum tensor, so it has character P. It does not mean that we constructed the energy momentum tensor of the whole theory. It can be quite easily that it is the energy momentum tensor of some subtheory. So hmm? It means that it is some combination constructed from this J diagonal, or it can be exponential of corresponding field. So it is something that expressed in terms of this sum of gi's. But what do you mean by charged? So it can, no, it can be. No, in a sense, it is something that is constructed from field J diagonal. So either some combination of its derivatives or some exponential. Yes, yes, e to I phi. Hmm? Oh, why? Just one or square root of n, sum of all phi's. Also, so it's a question what operators we should consider if we work with this Heisenberg algebra. But it is natural to also to add these vertex operators with arbitrary charges. So, mm-hmm. Yes. Oh. Yes. Mm. Mm, uh, but I don't remember. Did you check this or not? That so let us go back. Ah, uh, Actually, we have only half an hour, and probably we will not have time to finish uh, this computation for generic energy for generic K. Uh, so kappa is the question what it is. Let us consider the case K equals to 1. And let us even consider the case n equals to 1. Right? So we have the same contradiction even in this case, because we know that on one side there is the relation j of z equals to psi star psi. And then we have two energy momentum tensors. One energy momentum tensor is one half d psi psi plus one half psi star plus one half d psi star psi. And another energy momentum tensor is let's write it like this. Another energy momentum tensor is one half of j times j. So does it look like the same contradiction?
Okay, the dimension of the second one is not 2.
Why?
It's 2, okay.
Yes. So, but contradiction is the same, right? So, so let us see how it works. So we have this formula, which is quadratic in terms of fermions, and let us compute the OP of J and J. So, J of Z, J of W equals to psi star of Z, psi of Z, normally. So in this formula, this regular product means just normal ordering, because this fermions have numeric anti-commutator. Here we have psi star of W, psi of W. So there is a term in the OP where we pair this and this, and it is 1 over z minus 2 squared. There is a term when we pair these two. It is let us write common denominator z minus w, psi of z, psi star of z, psi of w. Plus it's for this term, and for this term it is psi of z, psi star of w. So let us move to different blackboard. Plus something. Okay, we also need to write the regular part, because we are interested in the energy momentum tensor. Psi star of z, psi of w, psi of z, psi star of w, psi of w, plus something. So Actually, so I wrote plus something, but there is nothing else because we are not re-expanding anything. It's just normal ordering. Plus normal ordering. Hmm? No, but here I'm using just this fermionic normal ordering for these computations, and I forgot to write it here. So it's simply the Wick theorem. And so term with one pairing, term with two pairings, term with one pairing, and term without pairings. So so this will be psi star of z psi star of w, psi star of w, psi of z, psi of w. So 1 over z minus w squared. And now we need to expand this around z equals w. So it will be uh, mm, mm, 1 over z minus w psi star of w psi of w plus psi of w psi star of w. So this is normally ordered. Plus the term with derivatives. So we expand the in z around w, so it will give d psi star of w psi of w plus d psi of w psi star of w plus let me write this regular at the end, plus this plus psi star of w psi star of w psi of w psi of w plus regular. So this is this for Fermat term you asked, right? So and what can we say about this term and also about this term? Mm-hmm. Yes. Yes, of course, because it is psi star of w computed at the same point, and it is under normal ordering. So this also vanishes. So we are left with this 1 over z minus w squared plus d psi star of w psi of w plus d psi of w psi star of w. But we can now write below that if we take the OP of g of z, g of w, it will be, by definition, 1 over z minus w squared plus normal product of j of w, j of w. So this is by definition plus all of So I wrote here. So I wrote here plus regular, but it's better to write it as all of z minus w plus all of z minus w. All of big O plus all of z minus w. So the conclusion is that normal product of j of w with j of w equals to d psi star psi plus d psi star. Or we can write it also as a normal product, because bosonic normal order coincides with normal product, because we simply remove the first order pole and look on the remaining expression. So we can write it as a normal product of d psi star times psi plus d psi times psi star. Yes, it is the definition. To compute normal product, we take OP of two operators, expand around the second operator, remove all singular terms, and take the constant term of this expansion. Uh, which normal order do you mean? But what do you mean by regular? They are all regular. What is singular? Mm.
So the product with the two dots and the product with the parentheses, the product with the two dots is just the one where you strip the singular part.
No. No. Product with two dots is defined entirely in terms of Fred-bosons or Fred-fermions, and it can be defined in different ways in this situation. So. So in total, we have three different products. And if we take some complicated operator, they any pair of them can, well, all three can give different results. So one. Fermionic, for example, or bosonic, because it was the first. We have some operators. So we have j of z, which is j plus of z plus j minus of z. So normal order or normal product of some let us write some polynomial of j of z, dj of z, d squared j of z, and so on. And let us denote this normal product by 3 dots. Not to mix it with the fermionic normal product. So let us write it schematically like j minus to the left and j plus to the right. So it means that when we compute a normal product of j of z cubed, it means j j plus j minus of z cubed plus 3j minus of z squared j plus of z plus 3j minus of z j plus of z squared plus j plus of z cubed. So we think that positive and negative components of some field commute, and just rearrange them in such a way. So is it okay? Mm, so yeah, let us let me think. So there should be some example where we should see the difference between these normal products. Actually, we saw it at some moment, but let us do this again. Let us consider the OPE of j of z squared with j of z. With j of w. So to achieve this bosonic normal ordering, we need to move positive modes of, we need to move negative modes of this j through this normally ordered expression. And it gives us two pairings. It will equal to normal ordering 2 times j of z, j of z, j of w. This expression plus plus simply normally ordered term. So this is 2j of z over z minus w squared plus j of z squared j of w. And then we want to expand everything around the second point. So it gives 2j of w over z minus w squared plus 2d dj of w over z minus w plus normally, let us write it as uh, oh, let's write the derivative. It will be d2 j of w plus normal order j of w cubed plus regular. So there is a third normal order, which is a CFT normal product, which takes this constant term in the OPE. So and this is precisely a definition. So this is a normal product of this j of z squared with j of w.
So that, sorry, there instead of regular, we mean order of z minus w.
Yes, yes.
This
Thank you.
equals to 0.
Yes, thank you. So it is a different expression. But if we think about j of z, if just j of z expanded with itself, j of z, j of w, it is 1 over z minus w squared plus normal normally ordered j of z, j of w. So it is 1 over z minus w squared plus normally ordered j of w squared plus all of z minus w. So normally ordered, so bosonically normally ordered g of w squared equals to CFT normal product. So is it fine? Mm, is CFT normal product? Oh. But it does not make sense because there are fields in different points. What do you mean by that? Sorry, I just missed the variable. Sorry. Uh, yes, sorry. So it is defined only for two fields in a point. Because if they are in different points, what would be the OP? So, so it makes sense to define this normal ordinals only if work with uh, some fields represented as some bosonic or fermionic zero modes. Actually, no. Probably uh, we can rewrite this CFT normal product in terms of modes and then generalize that formula formally. But if I understand correctly, it never appears in the real life. Because, mm, so, are there any questions about this two examples and about the definitions?
So in general, the CFT normal product, the normal product.
Yes, they equal only for quadratic operators. Maybe, no, maybe for some other cases as well, but there is no reason to expect that they are equal in general. Because what happens usually is that the CFT normal product takes some fields, probably some complicated fields, and that have their own mode expansions, and rearrange these modes as a whole. Like there are modes of this field, there are modes of that field, and they should be arranged in this way. Something is called creation operator, something is called annihilation operator, and they are arranged accordingly. But if it is a bosonic or fermionic normal ordering, it goes inside the internal structure of this field, and discover that it is, for example, some square or cube of boson, and breaks everything apart. So moves one field to the left and other fields to the right, and so on. And it is natural to expect that if we do something like this to arbitrary field, for example, if you take the Cosmology generators, for example, take their squares and then apply fermionic normal ordering, it can happen, and it usually happens, that such operator will not even lie in the Cosmology algebra. So we will be unable to construct it from the original fields. But this CFT normal product does not have such problems because it does not break the internal structure of fields. And it does not know anything about this internal structure. So it will give the same result independently on whether we realize some field in terms of boson or in terms of fermion. And for fermions, probably it is clear. So fermionic normal product, let us call it by two dots. It so takes some polynomial of psi star, d psi, d psi star, and so on. And again, it is psi minus psi star minus to the left, psi plus psi star plus to the right. For example, a normal order of d with signs. So a normal product of d psi star times psi of z, psi of z will equal to d psi star minus psi minus plus d psi star plus psi d psi star minus psi plus minus psi minus d psi star plus plus d psi star plus psi plus. Again, it knows about the internal structure of fields and um, breaks them into such elementary pieces and rearrange them. So is it okay? Hmm. And for example, what happens if you try to do something quite naive? For example, if you take this JFZ expressed in terms of performance, where is it written? Uh, yeah, it is written here. So what happens if you take a JFZ normally? If you take this JFZ and take it square and apply harmonic normal order ordering. So what is the harmonic normal ordering of psi star of z, psi of z, psi star of z, psi of z? So if you take a normal ordering of all this. Mm-hmm. No, I'm asking just that we have two operators, right? Hmm? Who is it? Oh.
Psi star W, psi W, normal order was zero.
No, psi star W, psi star W. So the problem was, so here the problem was that it was anti-symmetric and vanished because of this. But in the last term, it was zero because it was a square of something. Hmm? No, but here it is the same as this usual. Mhm. Mm-hmm. Yeah, but we can simply compute this. We just take OP of psi star of z psi of z and see that it's the only singularity. To remove the singularity, it's enough to normally order them. But so we have this operator that has some expression in terms of modes of Fermions, and in principle, we can apply this CFT normal ordering to such operators. In a sense, we can further arrange them. But we see that if we do this, we will get psi of z squared, psi star of z squared, which will be 0 immediately. So, and in principle, it is some bad operation. And this normal bosonic and fermionic normal products are useful only when we want to compute something in this particular algebra. And to write the answer in some simple form. But if we have so there but if you want to define something in terms of more elementary fields, for example, so we see that here it just gives 0 if we do it in this way. Sometimes we can get something that is not in our algebra. So, for example, if you put if you put here this normal order, and probably it will also give 0, although I don't remember precisely. Maybe no. Mm. Yeah, and also the answer will be different if we find some bosonic realization or harmonic realization. So. Uh, but it's also visible here because if we apply harmonic normal product, it gives 0. If we remember that it is actually a free boson, and it can be expressed in terms of bosonic modes, and apply bosonic normal ordering with this 3 dots. So 3 dots. Psi star of z, psi of z, psi star of z, psi of z. So this will give us the energy momentum tensor instead of 0. So okay, and let us think about the original question, and namely, what happens when we consider this energy momentum tensor with J expressed in terms of free fermions. So it will be normal product of psi star alpha, psi beta, psi star beta, psi alpha. So in principle, we could get quadratic fermionic so if alpha equals to beta, then we cannot get quartic fermions because such terms and the leading order should vanish. But now, what about the other terms? Mm, no. Yes, it was a correct question because if alpha and beta are different, we don't need to take this. We don't need to write this normal product here. we only need to multiply these fields. So probably it will be uh, uh, sum of psi star alpha, psi alpha squared. Mm. In a sense, it will be not the energy momentum tensor of uh, of Gaussian algebra. It will be energy momentum tensor without diagonal current. So. Uh, mm, Yeah, in this case, we can actually construct two energy momentum tensors. One energy momentum tensor is this one. Another energy momentum tensor is a sum of diagonal elements squared, because there is such a Yuan current that corresponds to identity matrix. And I don't remember precisely what precise energy momentum tensor is obtained in this way. Probably it is probably it will not contain this diagonal component. But let me think and tell it the next time. But in general, this energy momentum tensor will be that fermionic tensor, probably with something removed. And but we can write it also in such a way that it is just an energy momentum tensor of original fermions, because we have two pieces. We have this term, and we can also put here kappa prime over 2 in J1 of Z squared. Because a Gaussian algebra has two invariant scalar products. Because it is SLN plus GL1. So we can consider independently. So a scalar product on GLN in principle, we can write some kappa trace of AB plus kappa prime trace of A times trace B. And both of them are invariant. So is it fine? Or A and B? Maybe. Hmm? Mm-hmm. Yes, I'm just trying to see what kind of expressions we get from each of these terms. Because when alpha equals to beta, we already know that it gives something quadratic in terms of fermions. Because if alpha equals to beta, we have psi alpha and psi star alpha and psi star alpha here. So the leading term cannot be quartic in fermions. And the question is what happens in the off-diagonal terms. And probably the answer is that if we want to get an energy momentum tensor of original fermions, we need to also to take this term, which is which corresponds to this part of scalar product. So it should be sum of diagonal currents squared. It commutes with everything because it corresponds to a unit matrix. And probably if you take something like this originally, then we can lose on that term. So are there any other questions? Okay, if no, then thanks for your attention. See you the next week.